Hello, everyone. So last time we were looking at cardinality of sets, the concept of cardinality of sets. So last time, cardinality. Now, if you remember, we defined cardinality. When do we say that two sets have equal cardinality? Do you remember? So if you remember, we said that for finite sets, the answering this question is easy. We just need to count number of elements. But the main concern is when the set is infinite, then how can we compare the cardinality or the number of elements in two sets which are infinite? So we defined equality of cardinality of two sets. So we saw that, cardinality A equals cardinality B if there exists a bijection f from A to B. And you know that bijection means a function which is one-to-one and onto. Okay, now let's look at some properties of these cardinalities. So the first property is a property called the reflexive property, which states that cardinality A equals cardinality A for every set A. So later in this course, when we define relations, then we'll define certain types of relations, and we will see that one important type of relations is called reflexive relation. Reflexive relation means if every element in the set is in relation with itself. Now, in this case, the relation is equality of cardinality. So because every set, for every set, we can say that the cardinality of every set is equal to cardinality of itself. So that means every element is in relation with itself. For this type of relation, which, as I said, is the equality of cardinality, and therefore we can say that this is reflexive. So this property is called reflexive. We will define this formally later, as I said, in the topic of relations. Now, if I want to prove this, so it looks obvious, right? But remember, I always say in every class, many times in every class, that even things that look obvious still have to be checked according to the definitions. Now, definition says two sets have equal cardinality if there is a bijection between them. Now, what would be the bijection between A and itself? So if you want to prove this, note that f from A to A, f of x equals, how would you define a bijection between f set and itself? The easiest type of bijection we can define is the identity function. F of x equals x is a bijection between a set A and itself. So note that f from A to A, f of x equals x, is a bijection. Because it's one-to-one and onto, right? It's very easy. If you want, you can easily check that identity function f of x equals x is one-to-one and is also onto. And thus, cardinality A equals cardinality A. Now, second property is called the symmetric property. Symmetric property, again, we will define symmetric relations later formally, but for now, you probably can guess what it means. It means it's symmetric, meaning that if cardinality A equals cardinality B, then cardinality B also equals cardinality A. So if cardinality A equals cardinality B for two sets A and B, then cardinality B equals cardinality A. How can we prove this? Again, looks very obvious, but things are not as obvious as they look. Because cardinality A equals cardinality B according to the definition means what? So let's look at the definition. Cardinality A equals cardinality B if there is a bijection F from A to B. So please note the order. Cardinality A equals cardinality B if there is a bijection F from A, the first set, to the second set B. So here my assumption is cardinality A equals cardinality B. So by assumption, there exists a bijection F from A to B. And I want to show cardinality B equals cardinality A. So that means need to show that there exists a bijection, let's say G from B to A. So we're assuming that there is a bijection F from A to B. We need to construct a bijection like called G from B to A. What do you think G would be? Of course, it has to be something related to F, right? Because remember, we have absolutely no idea about what A and B are, what type of sets they are. It could be anything. Therefore, we cannot construct an explicit function because we don't know what A and B are. But we just know that there is a bijection F from A to B. So using this assumption, I want to construct a bijection G from B to A. What do you think that G could be here, could be defined as? We can define G as F inverse. F inverse, first of all, it exists, inverse function for F, because F is 1-to-1. Why is it 1-to-1? Because F is a bijection, and bijection means 1-to-1 and onto. All right, so F is invertible. Now, F inverse is a function from where to where, so that's the first thing we have to answer. F inverse will be from range of F, right? So domain, remember from pre-calculus, you know that domain of F inverse is same as range of F, right? Because the inverse of a function changes inputs with outputs. Every input becomes output, every output becomes input, right? So domain of F inverse, the set of inputs for F inverse is same as set of outputs of F, original F. So claim is that we can set a G as F inverse. So F inverse is from range of F to the domain of F, which is A. But range of F is what? F is, remember, F is onto. Onto means range of F is same as codomain. A function is called onto or surjective if range is same as codomain. What is the codomain here? Codomain is B, right? So range of F is same as B. So F is onto. That means range of F equals B. So F inverse will be from B to A. So that's the first thing. And why is it okay, so it seems there's a screen. Okay, yeah, here. So why F inverse is 1-to-1 and onto again. So that's another thing we have to show. So remains to show that F inverse is 1-to-1 and onto. So for 1-to-1, I think this was a pre-calculus question, one of the exercises, that if f is 1-to-1, f inverse is also 1-to-1. Why is it 1-to-1? So if f inverse of BA, let's say, equals f inverse of B. So let's assume that, for example, A is equal to f of, let's say x1, and B equals f of x2. Right? I think the screen is freezed. So let me stop share and share again. Okay. F inverse of A equals F inverse of B. I can assume that, let's say A is equal, because where is A and where is B? A is an input for F inverse. Input for F inverse is an output for F, remember? Input of F inverse, same as output of F. So A is an output of F, therefore can be written as F of some x1. Similarly for B can be written as F of some x2. Now F inverse of A would be what? F inverse of A would be x1. So then x1 equals x2. Let me draw a picture here. See, let's say A is in here. Let's say this is A, this is B. This is range of F, which is same as domain of F inverse. And then I have also, let's say, some x1 and x2 here in domain of F, which is range of F inverse. Now, for example, this is x1, and let's say this is x2. And then this is F. So F of x1 is A, F of x2 is B. F inverse of A, according to this picture, you can see F inverse of A is x1, F inverse of B is x2, right? x1 goes to A under F, and A goes to x1 under F inverse. Now, x1 equals x2, therefore F of x1 equals F of x2, and F of x1 is A, F of x2 is B. So I started with F inverse of A equals F inverse of B. After some type of reasonings and some middle steps, I concluded that A has to be equal to B. And then this means F inverse is 1-to-1. For onto, why is F inverse onto? How can I show that the function is onto? So F inverse, remember, is from B to A, right? So I have to take an element in A, because to show that function is onto, we have to take an element in codomain of the function and show that it has to be in the range. So take, let's say, A in A. Then F of A would be some element in B, right? Belongs to B. Say B equals F of A. F of A is in B, because remember, original F is from A to B, right? Original F is from A to B. So if I take some element A in A, F of A would be in B. I called it small b. Now, what would be F inverse of B? Thus, F inverse of B would be A. So I am repeatedly using the fact that F inverse, the main job of F inverse is to change input with output. for the original f, a is input, b is output. Small a is input, small b is output. So for f inverse, small b would be input, small a would be output. So b cos f of a means f inverse of b cos a. This is the meaning of inverse of a function, changes input with output. And that means a belongs to range of f inverse. If f inverse of b is equal to a, means a is in range of f inverse, right? That's the meaning of range of a function. And that means f inverse is on 2. Because we showed that every element in codomain belongs to the range of the function, therefore the function is on 2. That's it. So we showed f inverse is a bijection from B to A. So that's the proof of the property of cardinality of sets being equality of cardinality of sets being symmetric. Now another property, transitive. It's a property called transitive property, and which says that if cardinality A equals cardinality B and cardinality B equals cardinality C, then cardinality A equals cardinality C. So this is if a relation, in a relation, we can say that if A is in relation with B and B is in relation with C, then A is in relation with C. Then that relation is called transitive relation. So in this case, again, equality of cardinalities, cardinality A equals cardinality B, and cardinality B equals cardinality C, implies cardinality A equals cardinality C. And that means our relation is transitive. So how can you prove this? So proof, let me leave as exercise, but I can give you a hint. So let me tell you the path, what you need to show. So here cardinality A equals cardinality B. So what is the assumption? So let me write down the assumption, or assumptions in this case. Cardinality A equals cardinality B. Again, according to the definition, means what? Means there exists a bijection, let's say F1 from A to B. And the second assumption is that cardinality B equals cardinality C. So there exists also a bijection, let's say F2 from B to C. So what is the goal? To show there exists a bijection, let's say G from A to C. You want to show that cardinality A equals cardinality C. So that means you want to show there is a bijection G from A to C. So what do you think G would be in terms of F1 and F2? In the previous example, our G was F inverse, but here it won't be F inverse anymore. We have two functions, F1 and F2. So what do you think G would be? To show that if you want to go from A to C, how can you go from A to C? But F1 helps you to go from A to B, and then F2 helps you to go from B to C. So we can compose them. Composition of these two functions helps us to go from A to Z. So show that G equals, let's say, F2 composition F1, right? First, we have to apply F1 to go from A to B. Then we have to apply F2 to go from B to C. That means we have to consider F2 or F1 from A to C is a bijection. Okay, so I told you the path. The path is that to write down the assumption, give some notations to our bijections F1, F2, and then write down the goal and show that the composition can work as the bijection that we are looking for. All right, so this is another property. Now, another property of cardinality is that if A and B are countable, then A union B is countable. Okay, so and what was the meaning of countable? So recall, A is called countable if A is finite or cardinality. A equals cardinality of natural numbers, which we called it Aleph naught. Countable set means a set which is either finite or it has a cardinality of natural numbers. So we saw some examples last time. For example, we saw that the set of integers is a countable set because the cardinality of integers is same as cardinality of natural numbers. Although in beginning it may look a bigger set, but it's not bigger. Their cardinalities are exactly the same. Now, if I have two countable sets, their union will be also countable. How do you think I can prove this proof? So I want to consider different cases. I have two sets which are countable, but I know that each countable set has two possibilities, either finite or denumerable. If this happens, we saw that if cardinality A equals cardinality N, then we call A denumerable. So that's what we defined last time. So I have two sets which are both countable. So what are the possibilities? So I can say case one. One simple possibility is that both of those sets are finite. If A and B are both finite, then A union B is finite as well, right? And hence countable. So this is a very easy case. If both sets are finite, the union is also finite, of course, and the finite is always countable. Case two, a little bit more complicated or less obvious. Not complicated, less obvious. One set is finite and one set is denumerable. So if one set is finite and one set is denumerable, so it doesn't matter which one. We have two sets A and B, right? So let's say, for example, I can say A is finite and B is denumerable. Denumerable means cardinality of B is equal to cardinality of N. That's what I assumed. But of course, you can assume that B is finite and A is denumerable. The proof is very, very similar. So in the exam also, you don't need to prove both possibilities. One is enough. One set is finite, one set is denumerable. Let's say A is finite, B is denumerable, or you could do the other way. So how can I show that A union B is denumerable again? So I want to use a result that we showed last time. We want to use the result from last lecture. Which was saying that B is, or a set A is denumerable if and only if its elements can be listed. If the elements of a set can be listed, say as, for example, A1, A2, and so on, then that set is denumerable. And also conversely, if it's denumerable, then you can list the elements. Now my B here is denumerable, so I can list the elements, and A is finite. Of course, I can list the element of a set, elements of a set which is finite. So that part is obvious. So here, now let A equals, let's say A1 to AN, and B equals, A is finite. Remember, in my assumption, A is finite. And B is denumerable, so I can list the elements of B as, let's say, B1, B2, B3, and so on. Then, now I want to show that, what is my goal? My goal is to show that A union B is also countable. Now, if I can list the elements of A union B, then that means A union B is denumerable and therefore countable. How can I list the elements of A union B? Then A union B list means, tell me which one is the first element, which one is the second element, which one is third element, and so on. So of course, one easy way to list A union B is I can list first element as A1, second element A2, nth element AN. Then I can list B1, B2, B3, and so on. Right? So this is A union B, and we listed all the elements. First element, we listed A1, second element A2, nth element AN, n plus first element B1, n plus second element B2, n plus third element B3, and so on. So we listed elements of A union B. That means A union B is denumerable and hence is countable. So that's the proof for case 2. Okay, so then final case, case 3. If A and B are both denumerable, cardinality A equals cardinality N, and cardinality B equals cardinality N, then what can I say? Then I can list the elements of B and A, and also list the elements of B. Then A can be written, then A and B can be written as, so let's say A equals A1, A2, and so on, and B equals B1, B2, and so on. Now I want to list the elements of A union B. List means which one is the first element, which one is the second element, and so on. What do you think? So A union B, what would be the first element of A union B? Well, I could say A1, for example, right? So then thus A union B let's say A1 as the first element, what would you list as the second element? Well, if I list A2 as the second element, A3 as the third element, and so on, then I would have a problem, or I would be in trouble. Because A is not a finite set. So then when can I list B1? Is it going to be the 10th element, 50th element, 100th element? None of them, because A itself would continue forever. So before I lose the opportunity to list B1, why don't I include B1 as the second element? So second element, I want to include B1 or list B1. Now I already listed one element from A, one element from B. And then I can go to the second elements. Now, the next element, I can list A2, and next element B2, then A3, B3, and so on. See? All the elements of A and all the elements of B here are all listed. So first element of A union B is A1, second B1, third A2, fourth B2, fifth A3, sixth B3. So I have listed every element of A and B, and therefore every element of A union B here. I explicitly said which one is the first one, which one is the second one, and so on. So, and this is exactly what we mean by listing. You have to say, okay, which element is the first one, which element is the second one, and so on. So that means we listed elements of A union B, and then that means A union B is denumerable. And that means A union B is countable. Okay. Now that we have proved this property, we can show that the set of rational numbers is also countable. Please remember last time we showed that the set of integers is countable because denumerable. Now I want to show that not only set of integers, even set of rational numbers is denumerable. Set of rational number looks very big, right? But it is denumerable. So next, we will show that the set of rational numbers Q is denumerable. Denumerable means what? Means cardinality of rational number is same as cardinality of n natural numbers. This is somehow surprising, right? Many people would say, okay, if you want to compare infinite sets, probably we should say that rational numbers is bigger compared to natural numbers because there's so many elements in rational numbers, all the fractions like with top and bottom integers, 5/7 minus 8/9, all these things. But in natural numbers, we just have 1, 2, 3, 4, and so on. But these two happen to have equal cardinalities. How can I show this? So the proof is in few steps. I want to prove this in few steps. Step 1, cardinality of n cross n is equal to cardinality of n. N cross N means the set of all pairs, right? Recall N cross N means what? A cross product of two sets. Can be written as all pairs, let's say A and B, such that A belongs to N and B also belongs to N, which is going to be like 1 and 1, right? 1 and 2. Okay, how can I show that N cross N is denumerable? I want to show this by listing elements of N cross N. So we will show that N cross N is denumerable by listing its elements. Listing elements means what? As we did in the previous case, example or property, means which one is the first element, which one is the second element, and so on. So what do you think I can list as the first element of N cross N? So first element, but you could probably suggest that 1 and 1 can be listed as the first one. Okay, what about the second element? Could do 1 and 2. Third element, 2 and 1. Then fourth element, I want to say 1 and 3. Fifth element, I want to say 2 and 2. Sixth element, 3 and 1. Do you see the pattern? How I'm listing them? The first one, 1 and 1, then 1, 2, 2, 1, then 1, 3, 2, 2, 3, 1. So as you have maybe guessed, the pattern that I'm choosing to listing all these elements is that I will look at the sum of the two numbers that I have. Remember, I have a pair, therefore I have two numbers. I will look at their sum. The minimum possible sum is 2, which happens only for 1 and 1. So this one C has the sum of 2. So first we listed the element with sum of 2. Then we are looking at the second and third, then listed elements with sum of 3. One and 1 has sum 2, 1, 2, 2, 1. These two are the only elements which have sum of 3. Then we looked at the elements with sum of 4. Listed elements with sum of 4. And so on. So as you can guess, the next one. And among all elements which have sum of 4, we start with a pair whose first coordinate is 1. And then the pair whose first coordinate is 2, and so on. So you can probably guess that the seventh element is, so sum of 4 is listed already. Now sum of 5. Sum of 5 could happen as 1 and 4, for example, right? And then the next one, 8, 2 and 3, 9th, 3 and 2, and 10th, 4 and 1. So these have sum of 5 and so on. Okay, so this way we are listing every element of n cross n, because every element of n cross n has is a pair, and therefore the sum is some number. The sum of those two numbers is some number. For example, it could be 51. Then it would be somewhere in this list, right? So we are listing all elements of n cross n, therefore we listed elements of n cross n. That means n cross n cardinality is equal to cardinality n, and that means n cross n is countable, enumerable, and therefore countable. Okay, this was step 1 to show that the set of rational numbers is countable. Now my second step, step 2, the set of positive rational numbers is countable. Cardinality of positive rational numbers is same as cardinality n.